Okay, so we can isolate an amine, add the amine to an acid chloride. It can be a primary, it can be a secondary, it can be ammonia. It doesn't matter, they're all going to do the same thing. We've drawn this mechanism before where the amine nitrogen adds the carbonyl, you break the carbon oxygen double bond, sending them to the oxygen, reform, kick out the chlorine, and then with our extra amine, whether it's ammonia or some primary amine, the extra amine grabs the hydrogen to give us our amide. We can do this with as a protecting group on the ring, or maybe not a protecting group, but to slow down the reactivity, because if we have an aromatic ring, we know aniline is very reactive because the lone pair on the nitrogen, it can only be sent into the ring. It's not delocalized any other way. But if we add the acid chloride to that and make acid anilide, then we can also think about the resonance structure where we send the electrons on the nitrogen away from the aromatic ring. So it cuts down on the amount of electron richness that the amine gives to the aromatic ring. So we can only brominate acid anilide once on the pair position, and then we can cleave the amide off, and we can basically do over a couple of steps, take aniline, parabrominate it cleanly, as opposed to if we just took aniline and tried to do this, we end up getting all three positions brominated, so it's not what we want if we only wanted the pair position brominated. So we have to be careful what we do so that we control what happens in all of the reactions. So another thing about aniline in general is we know aniline is an OP director, but depending on what type of reaction we do to it, we can make it a withdrawing group also. If we tried to alkylate it, adding the aluminum chloride, the nitrogen reacts with the aluminum to form this group off of the aromatic ring, which has a positive charge on the atom right off of the ring. So we know that's going to be a withdrawing group. So that would react meta if it put anything on there. We can't put the methylamine on there. Nothing will happen there. But if we take aniline, make the acid anilide again, then we can alkylate it on the pair position, cleave off the amide bond, and we have cleanly alkylated the aniline to make the paramethyl-aniline. Okay, so protecting the nitrogen, making it the amide, cuts down the reactivity, gives us more options on what we can do on the aromatic ring itself. Now, we can eliminate an amine just like we did with alcohols under certain conditions. To do this, we have to make the amine a good leaving group. To make it a good leaving group, we have to get the nitrogen with a positive charge on it, so we can over-alkylate it with methyl iodide to give us as many methyls on the nitrogen as we need to get it positively charged. In this example, we need to put 3 on it to go from the neutral primary amine to the quaternary ammonium salt, so we can eliminate it. Okay, and the quaternary ammonium salt, the nitrogen has a positive charge, so when it leaves, it's going to leave as a neutral nitrogen, which is going to be a decent leaving. So with this, we can add hydroxide. It does an E2 elimination. The hydroxide grabs a hydrogen, forms a double bond, kicks out all the trimethylamine, and we're done there. The overall reaction sequence is shown here, where we add excess methyl iodide and then follow it up with the silver oxide and water and heat, and it does the E2 elimination. We got to remember syn or anti-coplanar arrangement of the hydrogen in the leaving group, depending on which bond we're looking down. We have to be careful about that. So we might as well draw in our hydrogens on carbon 3 and carbon 2 in such a way so that we draw, or carbon 1, so that we draw them as far apart from what becomes our leaving group as possible. So if we think about the bond carbon 2,3, with the way it's drawn right there, we really need to rotate the methyl around 180 degrees. So if we redrew it, it would be something like this, with the hydrogen and the carbon off of that wherever. So if we put our eyeball here, looking down the 2,3 bond, we would see the way it's drawn here, which is the lowest energy conformation, with the methyl and the nitrogen as far apart as possible. Looking at the Newman projection, the carbon in front, the carbon in back. Nothing is no hydrogen is anti-coplanar to the nitrogen, so we would need to rotate 120 degrees, redraw again, nitrogen, hydrogen, carbon in back, and then in front we'd have hydrogen, we'd have carbon. So on this one we could eliminate with the carbons on the same side, or we could draw it, also rotate, since we have two hydrogens on that carbon, leaving the nitrogen in back the same. We could rotate the carbon in front to that side, put a hydrogen there and a hydrogen there, and when it eliminates, we could get the carbons anti to one another, or trans to one another. So both of those are possibilities. The main product is probably going to be the one with the carbons trans, if it were to eliminate that way, just so the carbons were as far apart as possible. Now if we look at the Newman projection, when we look down, let's change it to blue, look down this bond with our little eyeball, carbon in front has 3 hydrogens. The carbon in back has a nitrogen up. Then we could draw this to one side, that to the other. And we have 3 hydrogens on the front carbon, so it's not going to matter where we draw them, because they're all the same. We're going to get the double bond on the end that has 2 hydrogens there. Okay, so we remember nitric acid from Gen Chem. Nitrous acid, H2, or HNO2. Okay, it's not as strong of an acid as nitric acid, but it gives us something that we could do things to. So the way to it's formed in the reaction, so we usually use NaNO2 and HCl in our reaction. So we form the nitrous acid, but how to do it, we have HCl, we protonate the OH again, which makes it a good leaving group, and then we can use the electrons on the other oxygen, and we form the nitrosonium ion here that we see. Okay, once we have it gives us the freedom of being able to use the nitrogen of our primary amine on it, and this needs to be on an aromatic ring to attack that nitrogen. We drew the other resonance structure with a triple bond to the oxygen, sending the electrons to the oxygen. So the first step of this gets us to this, and we'll switch to the next page and continue on drawing it. That gets us there, and in the end we want to get to a triple bond between the two nitrogens. So we see two hydrogens on the one nitrogen and the oxygen on the other one that we're going to eliminate off as we go along in this process. So the mechanism, as talked about in the first step, the nitrogen of our aniline attacks the NO plus ion. In the first step, so we form the nitrogen-nitrogen bond. Then we remove the extra hydrogen off of our nitrogen. We need to protonate the oxygen because we need to get rid of it. So we need to somehow get hydrogens on it so we can kick it out. We can draw a resonance structure moving the positive from the oxygen down to the nitrogen, hence the resonance arrow there. And then with the positive on the nitrogen, we can remove the extra hydrogen with another equivalent of water to get us to the N neutral, and then we can protonate our oxygen because we know it has to leave at some point, so we need to make it a good leaving group. And then we can just send the electrons from the nitrogen down to form the triple bond, kicking out our water, and there we have the diazonium salt. And that is a very reactive species that we can do a lot of things with. So if we had a secondary amine and look back at that mechanism, it would stop at the nitrosoamine because it can't go any further. Okay, this reaction is usually only done with aniline or substituted anilines to form the aryl diazonium salts. So in this, we take aniline, we make the diazonium salt, and then we can do something with it to displace the N2 on the aromatic ring with any number of things. And all of the things we can do, we can put a bromine on it, we can put a chlorine, we can put an iodide, we could put a nitrile, a fluoride, an OH, or we could reduce it down to the hydrogen. Hey, now for this, you should know that the only way to form the benzonitrile or phenol is this way that's approved in class. Do not try one of the ways in the book where it says take a chlorobenzene and add water and heat it. That doesn't work well. Don't do it. We need to make the diazonium salt and then add water to it. Okay, and these are the main things we can do. Yeah, we learned a long time ago we could brominate benzene with iron and bromine to get it to go on benzene also, but this gives us another way to get there if there's something else on the molecule that would cause problems with bromine and iron. So this is very important. The only way we can make phenol is we nitrate the ring, we reduce it, iron and HCl, and then make the diazonium salt. So we nitrate the ring, make the NO2, reduce it to the substituted aniline, And then from there, we can do NaNO2 and HCl to make the diazonium salt. And then to that diazonium salt, we can add water and heat and make this substituted phenol. These 4 steps are the only way I will give points on a test. The only answers I will accept for making a phenol. If you need to make a phenol anywhere, you need to do this process. When treated with hypophosphoric acid, the diazo group is substituted by a hydrogen. So we could think of it, we can nitrate, reduce. So steps 1 and 2 would get us to just aniline. And then the aniline we can brominate to get there. And then we could reduce make the diazonium salt and reduce it. And we've added the bromines on 1, 3, 5 to each other. So bromine by itself is an orthoparadirector. So if we put 1 on, we're not going to be able to get this pattern on if we just did bromine. But having the aniline on there and then brominating that, we can get the bromines 2, 4, and 6 to the aniline, and then reduce off the nitrogen, and we've created something different than what we could have done any other way. The other thing we can do with the diazonium salts is we can make a diazo coupling where we end up with a nitrogen-nitrogen double bond in between 2 aromatic rings. The ring that attacks has to have an R group on it that's a good donating group. Okay. So alcohol and methoxy, an alkyl group, and nitrogen, things like that, so that it goes as an electrophilic aromatic substitution where the diazonium salt is our electrophile, much like what we did with Br2 and iron back in chapter 17.